Welcome to our presentation on the emergence of adversarial communication in multi-agent reinforcement learning. Multi-agent systems are becoming more important in our day-to-day life. Warehouses are automated and autonomous driving is becoming feasible. These tasks often require communication, but if all agents assume cooperation, a faulty agent can disrupt other agents. In more sophisticated adversarial scenarios, agents can be optimized to cause damage to cooperative systems or to manipulate them to reach a self-interested goal. For the warehouse example, this can severely affect the supply chain and cause major economical damage, and in the case of self-driving cars, even cost lives. Being able to learn such adversarial communications is the first step towards developing mechanisms to detect and mitigate them. On the top, we see a grid world populated with cooperative agents that solve the cooperative pathfinding problem. Graph neural networks promise the learning of decentralized cooperative communication strategies. In complex multi-agent settings, the optimal strategy is often unknown, making reinforcement learning an attractive tool. On the bottom, we see how adversarial communications of a single self-interested agent interferes with cooperative agents. We introduce a new learning model using individual non-shared rewards and focus on the self-interested case. We develop a learning algorithm to show the emergence of adversarial communications. We consider a set of cooperative agents that share a homogeneous actor neural network that utilizes a graph neural network for inter-agent communication to predict an action A given an observation Z. A centralized critic takes into consideration each agent's observation Z and a global state S and outputs a value function estimate V. The interactions of those components can be seen on the right side. The homogeneous aggregation GNN formulation takes into consideration the graph shift operator S, which in the simplest case is an adjacency matrix, a feature vector X, and a set of weights H for each communication hop K. We extend this formalization with a heterogeneous AGNN so that each of the N agents can have a different set of neural network weights H. Note that both AGNNs can be trained centralized but executed decentralized. We first train the cooperative policy with state-of-the-art policy gradient. For the self-interested training, we freeze the cooperative policy and modify the policy gradient so that the self-interested agent estimates its advantage with respect to all cooperative agents. We verify our model and learning algorithm with 3 experiments. First, we consider cooperative path planning in non-convex environments. From this experiment, we derive the split coverage, in which agents only receive a reward for covering the right side. Agents are represented as squares and can communicate to other agents within communication range. Black cells represent obstacles and colored cells represent the coverage of all agents. Lastly, we had a path planning experiment in which each agent has to reach its goal as quickly as possible. We evaluate the performance of our approach by comparing the average performance over 100 evaluation runs for the self-interested agent in red and all cooperative agents in blue, both with communication between the self-interested and cooperative agents enabled in solid lines and disabled in dashed lines. We can clearly see that with communication between the two groups enabled, the self-interested agent is able to obtain a significantly larger fraction of the return than cooperative agents. In contrast, if communication is disabled, this is reversed and the cooperative agents outperform the self-interested agents. This same pattern can be seen for the split coverage and path planning experiments as well. Lastly, we use a post-hoc interpretation method to visualize the information encoded from the local observation of each agent, which is the message that is communicated to other agents. We compare for the self-interested agents on the left side and cooperative agents on the right side both the true local observation and the decoded message. We can see how the decoded message for the cooperative agents reflects the true observation as indicated by the high mean average precision, while the decoded message of the self-interested agent does not reflect the true observation. This means that the self-interested agent communicates adversarial, even manipulative information, whereas cooperative agents communicate truthful information. We introduced a model and learning algorithm that is capable of accommodating multiple agent objectives while maintaining a common differentiable communication channel. We are the first to show how to set up a learning system that allows the emergence of adversarial communications, which we analyzed using a post-hoc interpretation technique. In future work, we would like to perform co-training of self-interested and cooperative policies and research methods to detect and mitigate adversarial communications. Thank you very much for your attention.